I'm going to introduce Lisa. She is the new employee in my department. She's working for institutional research and learning a lot. So I thought this would benefit her.
Hi, everybody. Thanks for letting me sit on.
Oh, no problem. Dr. Li, I don't have permission to share, so it's kind of hard to share the slides, but
okay, let me see.
Thank you.
There you go. Before we get started, I think I want to take a few seconds to introduce you. So Ian Bowler, I'm glad to have him as my student advisee for, I think, 3 years, right? This will be the 3rd year since I joined E-Town. He's actually on my search committee when people are hiring me. So glad to have you. And today, Ian Bowler is going to present his honor thesis in the discipline of data science, titled as Analysis of Applications and Matriculation, a Machine Learning Approach. So Ian has been working on this thesis starting from this semester, and the idea was actually long before this, right? If I remember correctly. He always has the passion to do something for the college, in terms of doing data analysis or doing something else. So please join me to welcome Ian Bowler for his thesis today.
Thank you. Yes. So the assignment was to do something that benefited a business, and the closest business I could find was the college. So that was what I chose to my topic, and that's when I started back in January. I approached Deb with the topic idea and began from there. All right. Let's see. Is my screen sharing? Okay. All right. So start with the background. So there's why is it not? There we go. I have to click. I can't use my arrow keys. All right. So significant research does already exist in academia in terms of forecasting totals in admissions. So that would be like your total incoming class size and the total number of applicants, things like that. So that's a pretty straightforward thing to do. That's performed often, but that's not really what this is about. This is more about being able to predict whether an individual student will choose to deposit at the college given certain characteristics determined by their application, information that they've provided, and other information that we may know about them. So commercial products do exist that serve this purpose, and they usually integrate with the actual admission software that colleges use. However, there isn't really much existing research in academia regarding this, and that does not have the same data dimensionality as we do. So they're only focusing on a few characteristics of the applicants and not as many as we have. And another thing is that feature engineering has not been researched to any large extent in this domain. And feature engineering is where data about a certain record is used to extract and generate new features that were not there in the original data set, but may provide purpose in terms of training the model and further analysis. So the project objectives were to extract, transform, and format the admissions data for visual analysis and for classification model generation. The data was extracted from the college's enterprise resource planning Genzabar system and had to undergo various transformations that will be discussed later when I get to the data collection section. So another objective was to demonstrate and evaluate techniques for the feature selection, analyze the impact of class imbalance on the model performance. You'll see what I mean by class imbalance slightly later. And comparing the accuracy of different types of models and the prediction of an applicant's inclination to deposit and matriculate to the college, and the use of these models as a potential explanation of applicants that would be most likely to matriculate without knowing that status in the future. So based on the information that we receive from an applicant who we've accepted, whether or not they will choose to deposit. So addressing data availability. When you have a large data set with multiple features, it's possible that some of those features will be unavailable for certain records. Solutions for solving this are something called imputation of values, which is using either statistics or common domain knowledge to fill in those missing values. Other options are excluding of the records that are missing data, or excluding of the features that are missing data for certain records. Another concern with data availability, especially with our data, is that the data for GPA and class rank did not have scales. So it's possible that that data could be on a scale of a 3-point scale, 4-point, 5-point, 6-point, 50-point, 100-point. So it's kind of hard to use that as a reliable measure. But I did attempt to standardize those scores in a way that was relevant enough that the models detected that as a significant feature, that sort of reverse engineered GPA score that I was able to come up with. So another concern that I addressed in this project and analysis was the curse of dimensionality, which is where training models with many features is computationally and memory intensive. So although there were only about 30 different features in the data set that I collected, each of those features, the categorical ones, had several different values that could be used. So when you transform that into a format that can be used to train models, the dimensionality grows significantly, getting about 600 features at least when you do that. So another problem with this curse of dimensionality is that more samples are required to effectively train models and address multiple occurrences of each feature combination. So in order for the model to be accurate in predicting a certain type combination of features, it needs to see more examples of that. So there are some techniques for reducing dimensionality to expedite this training process and reduce the resources required. One of these is principal component analysis, which uses matrix algebra and eigen decomposition to transform the basis of the data, and then only the most significant components are selected. But the problem with this is that it obfuscates the original features, so it makes it harder to, it increases the complexity of model interpretation and makes it harder to explain what the model is doing in terms of the original features, which is one of the goals of this project. So instead of that, we do something which is called feature selection, and that uses statistical evidence or domain knowledge to determine which features to use. Forward selection and backward elimination are two techniques. Forward selection begins with no features, and the features are gradually added to the model until there's no improvement in the accuracy. And backward elimination begins with all features, and they are removed until there's no gains in accuracy. So forward selection is less computationally expensive than backward elimination. So some other options for this feature selection are using the models themselves. Decision trees can be used for this based on the separability of split value, which determines which feature is most important in splitting the data into different segments. And also logistic regression can be used for the sake of feature selection when all of the input features are standardized, and then the coefficients, actually the absolute value of the coefficients for logistic regression, can be used to provide an insight as to the importance of these features. Discussing the class imbalance problem. So if classes are imbalanced, it influences the model's tendency to predict the majority class. So if you have more people that deposited, so say 80% of the people, sorry, say only 20% of the people who were accepted deposited, then your majority class is people who did not deposit or chose to withdraw or defer. Sampling is a technique for combating this. Oversampling the minority class or undersampling the majority class. These each have some drawbacks, being that oversampling increases the potential for overfitting by causing the model to see the same examples more than once. Undersampling has a potential for information loss, as you may lose some of the majority class examples and train towards a potential biased sample from that majority class. Other options are using weighted cost functions, which create penalizations for misclassifications, and a boosting technique, which is iterative weighting of misclassified observations, such that several smaller models work together and grow into a better model that is more sensitive to these to the imbalance in classes. One of the drawbacks to this is that it's sensitive to outliers and noise. So here we can look at the data that we have. Up top is the training data set, which was 2009 to 2017, and below is the testing data set, which was 2017 to 2020 data. As you can see that out of the applicants, we had more people accepted than declined. And then deposits, this is deposits out of the total applicants. And then this is deposits given acceptance. So deposits given acceptance is the main thing we're trying to predict here. So that would be matriculation to the college given acceptance. And in this case, we have a class imbalance in the opposite direction where more people are choosing to withdraw or defer than deposit. So here's just a diagram showing gradient boosting trees, which are used in this extensively. And that just shows that trees are fitted in a process, and the loss function, which is differentiable, uses gradient estimation and calculus to determine the residual input for the next fit of this decision tree. And then the final model is produced through this process. So data validation, some of the things that I experienced looking at the data was I found that there were, in the very beginning, we found some issues where there were multiple records for the most recent high school of a single applicant. So that we had to go in and correct the data there. We also had application incomplete records that were dated after application complete records, which doesn't make any sense logically there. And we also had duplicate candidate relationships where somebody had the same grandparent listed 20 or 30 times. So here was the data collection model, moving from the database, performing table calculations, adding supplemental details, performing pivots, extracting the data, providing it to Tableau to transform and visualize, and using Python, Pandas, Scikit, PyTorch, and XGBoost tools to build candidacy models with predictors and to determine the trends from those. So just showing some of the transformations that needed to be done. SAT and ACT scores were listed in a vertical format and needed to be transformed into a horizontal format so that each candidate record had all of the scores provided there instead of multiple records for each candidate. And the same had to be done with the different application statuses. Another part of data transformation was that there were inconsistent formatting and availability of geographic properties. So some records didn't have a country, some records didn't have a state, some didn't have a zip code, things like that. So this during the dimensionality reduction step, this was needed because if you were to keep all of the features of the address, each address would be a unique feature of the one-hot encoded data used to train the models. So I used the Bing Maps API to transform the city, state, province, zip, and country into lat-long coordinates. And that's something that's easier for these models to handle. And I also did a feature engineering to calculate the distance from the college using spherical coordinates. So you can see here, calculating the distance to some place in Australia using those coordinates, finding the closest radial distance on the Great Circle. Finally, I grouped the inquiry sources. Some of these sources were duplicated. People applying through similar online methods or inquiring through similar methods, we had different names for the same category in there that needed to be grouped. I converted ACT scores into SAT scores. Luckily, all the SAT scores were already on the 1600 scale, so I didn't have to worry about dates there. And I only kept the best score in terms of training the model. So here I can, I also mentioned again the GPA scale estimation that was performed to try and recover the actual GPA data. So here I have showing the variable significance as determined by decision tree and logistic regression models for accepting a student. So this is based on a student applying, whether or not we accepted them. So here's what the statistics said, were contributing factors to that. So not clearly admissible being an admission rating was significant in determining whether we would accept a student, as well as GPA, SATs, whether they were denied to the OT program, class, the latitude, longitude, distance, whether they were choosing OT as their intended major. You can see over here that logistic regression found some interesting things. If their top choice of college was Lehigh University or Rutgers University, those were statistically influential factors in this basic logistic regression model. But this was just for acceptance. We can move on to what we were really trying to study, which was deposit given acceptance. So I have here from decision tree, logistic regression, and random forest, the different results. And having race or ethnicity unknown was the top feature across all of these. You can see that 2 of these included visit to campus being yes, which is one of the features that I would predicted would be important in terms of this deposit. And some of the other ones are slightly interesting: religion and high school type, honors program status, and interview status, whether or not they had an interview. So I also did variable significance using XGBoost, which determines it in a different way, a slightly different way. And it provides different scores, but here we saw that engineered GPA feature was actually seen to be the best feature, most significant feature here. And variable significance using XGBoost is determined by the interclass versus intra-class variability. So I did different models: logistic regression, ridge classification, support vector machines, decision tree classifiers, random forest classifiers, XGBoosted tree classifiers, naive Bayes, and neural networks. So each of these different models needed to be evaluated, and typically evaluation is done using accuracy or something like precision. But in the case of this imbalanced data, we need to use some more complicated metrics in order to account for the imbalance. So specificity is the true negative rate. So that's out of all of the negative examples, how many of them are negative. Recall is the true positive rate. Out of the positive examples, how many are positive. A balanced accuracy score was what I ended up using in the analysis to rank these models. And that's really just a combination of the true positive rate and the true negative rate. So true positive rate plus true negative rate divided by 2 is that weighted score there. Another metrics that was used was the F1 score, which is the harmonic mean of the precision and recall, which are these 2 metrics. Also, in terms of some of the cross validations that were performed, the area under the ROC curve was calculated. And this is where you want to see that a model is performing well. The true positive rate is high, and as the false positive rate is high, it remains the same. So we definitely want our model to be better than the expectation for random guessing, especially because since it's a binary classification problem, and random guessing doesn't really help us that much. So just wanted to show the results of the worst and best model in terms of classification here. You can see that the naive Bayes model performed the worst, having a lot of false positives here in terms of deposits. In fact, the largest category was the false positives here, which was very significant. And then here I have the linear support vector machine, which performed the best in terms of all of the models tested. So I have a table here just showing all the results, so you can see where things fell in line. So SVM was the top 2 here. The third option was one of the gradient boosted trees. The fourth was a logistic regression model, and the 5th was one of my neural networks that was designed. So this was the single layer neural network with 5 nodes in a single hidden layer. Some of these descriptions down here, this chart is available in the written copy. I just have explained here what sort of these symbols mean. So this is a feed forward 5 node center stochastic gradient descent model trained with 100,000 epochs. And then finally, I have a Tableau demonstration on some of the analytics that I did. And so here I can show so here is one of the things that I thought would be most important, which is visit versus deposit. So here are the people who visited the college, whether they deposited versus deposit down here and not deposit. And the opposite here, it's interesting that in 2011, it seems like we had an increase in visitors. So deposits and acceptances over time, it's just showing that we've been accepting less people over time total, and that the number of deposits has remained about the same. So then here I have distance from campus and visit status versus deposit. So here is, this is on a logarithmic scale. showing where people had either no visit and did not deposit, no visit but enrolled in some of these further away areas is pretty interesting, and then visited and enrolled. You could see that people who were 7 miles from campus, all of them visited and all of them enrolled, which was interesting. Just looking at the variation in the SAT scores of accepted students over time. Here seeing the deposits by SAT score. So it's just showing that these lower SAT score people seem to be more inclined to deposit after acceptance. Looking at here, the difference in the distribution of SAT scores for the deposits versus non-deposits for a given year. You can see there are some years where the deposits were greater than the non-deposits, and other years where it was the reverse. Just looking at areas, sort of a heat map across the United States, these are areas where people chose not to deposit. So it would be just interesting to see what's going on, in these sort of hotspots, why they're not depositing. But it's also possible that these are just clusters where we actually saw students. You can see the same thing across Pennsylvania. Looking at percent of each class size deposits, it seems like we had smaller amounts of larger class sizes. It's about the same for some of the mid-range class sizes. Looking at deposits by race, it seems that race or ethnicity unknown, most of them did not deposit here. Looking at gender, a more percentage of males deposited than the females. Looking at departments, the occupational therapy department, more people deposited than not depositing. Looking at different high school types, public high school was the greatest there. And then here we're looking at the results of the best SVM model, which ones were the model predicted it correct. So this would be true positives and true negatives versus false positives and false negatives in red. And then looking at that by distance, by race, religion, high school, correct, by SAT score and class size. So I just went through a bunch of different various things that I thought would be important in terms of these models, and saw in which ranges of those features where the model was accurate and where it wasn't. So I can try to provide some of these charts as an export. I don't know how interactive they can be without having Tableau licenses for people, but I can provide the basic charts. So just want to end that with any questions.
So what's the takeaway for admissions or marketing, I guess?
Yeah, the data could be used to benefit either the admissions or marketing departments.
How?
How? So you could be able to see. Oops, where'd my presentation go? So if you look at which features are important, this would give you the option to take a given applicant and determine whether if an applicant has these features, it's likely that they're going to deposit, but it would be something that we would want to spend sort of pressure on the students who don't have these characteristics, who were accepted, that applied, perhaps to try to convince them to deposit.
I mean, so I wanted to get you a little bit outside of your comfort zone here. Here's the thing, right? The data we have is the students that we dealt with. And we keep saying, well, I don't know if you hear much of this chatter, but there's a lot of talk about us trying to find new markets and trying to find new students and we talk about diversity without having any and things like that. So, which then says that, well, your predictions are based on our historical, efforts, historical advertising, historical, I don't know, reach in terms of high schools and geographic things. what would you say the usefulness of this is if we were to think about broader markets, different student?
So you could look at combinations of things like SAT scores and interests and forms of response, and use those to try to determine other markets. So if you're seeing people with SAT scores in this range in Nebraska who are interested in data science or something like that, or who come from a school with a small class size, they might be interested in coming here. So those would be maybe schools that we could target in terms of advertising or things like that. And another thing that would be possible as an extension of this, I didn't choose to pursue this, but one of the things that Dr. Li and I discussed was the potential of trying to use social media information online to determine which, sort of students, high school students would be, fitting with the goals and interests of the college.
Ian, you did a lot of work, and there's so much that goes into all of this. How accurate, if you knew what you knew today, what would you be doing different? What would you have done differently?
I definitely would have done more in trying to make sure that the data was valid to begin with. So trying to do things like find the actual scales for those GPAs. It would be nice if the college had that information just for our own sake to be able to know, where these students are coming from. Sort of the class rank was another thing that was sort of not uniform across there and just had to be removed from the data entirely. Just looking at the addresses, seeing this stuff in the data, the number of times that they've been changed and how they're wrong. And, we had people that were in like New Jersey in a different country. It just didn't make sense. So in terms of cleansing the data, that's definitely an important thing. Garbage data in, garbage model out is one of the biggest things. So I tried my best to remove the garbage from the data, but there's definitely still some garbage in there. Another thing that I would have done is in terms of the models themselves, I would have spent more time and effort training them. So the SVM model that came out was just the base model, because the SVM method is one of the slower of these methods. It takes more time to do. So just training the one model took like 15 minutes, and I had to do that like 4 or 5 times for the different sets of data, and then repeat to make sure that I wasn't getting any random variances. So it probably took just like 2 or 3 hours just training the 4 or 5 different SVM models that I tried.
Did you give any thought to why ethnicity unknown is so high in the importance?
So I'm thinking that the people that chose to not report it may not have cared as much. Is one of my potential guesses to that. I think that there was actually, isn't there actually an other category that's different from unknown?
Yes. Yeah. I don't know if you did this, but when I looked at that, I'm like, oh my, there's something wrong there. But just from knowing the data a little bit more intimately than you, what I would think is that there's a possibility that maybe we should have time stamped the race and ethnicity based on when did they apply, what was the race and ethnicity at that point in time, at the accepted point in time, and at the deposited state and time. We didn't do that, did we?
No, we did not do that. And I did not mention this. I forgot to mention it in the paper and in the presentation. But one of the things that Deb and I looked at the beginning of this semester was address of the student. So if a student applied at an address and then moved, the new address was what was being pulled originally. So I had to go in and change that. And it's interesting. I found myself as an example of that. I looked at my own record in this data set. I'm in the testing data set, of course. And I saw that my address didn't match the address that I used when I applied. And I said, well, something's wrong in this data. So I had to go in and figure out all of the SQL necessary for that, to look at the historic address table and find, based on the date of application, what the most recent address occurring before the date of application was. So that was another interesting aspect that I completely overlooked. When I was going through the data variation analysis, to put that into the paper and the slides. I was looking through all my emails with Deb, and I guess that was one thing we discussed over Zoom and not by email, so it missed the list in terms of things that I found in the data.
That was good. And how do you think using as your training model classes, using from 2009 to 2017 affected your results?
So I think it definitely affected the results in the fact that we changed the way we're collecting data. More recently than that, though, I believe that was 2018, right?
Yeah.
That we changed the way we're collecting the data. Well, the most recent change.
Yeah.
Yeah, there were other changes occurring before that. So one of the things that I noticed was in terms of the source description, the applicant source. So where the applicant first heard about the college, a lot of those changed from year to year because our sources of gaining applicants and interested parties changed throughout the years.
Very good. On your charts that you were showing the results from, did you include just 18 to 20, or does that include your training course classes as well?
So these are just the training. These are just the testing data here, showing the accuracy there. I could go back and get the accuracies, for the model based on the training data, but it's in most cases it's significantly better, something like 98% or 96% in all of these cases.
Yeah, in the if you zoom ahead like a bunch of slides, those charts where you were showing, yeah, and more more toward the back end of your slide. So yeah.
I think that's the table with all the other models.
You want the full data?
Yeah, keep going.
This one?
Yeah, no, more. Keep going more to the end where you were showing.
There's nothing further than this.
Oh, isn't there? There were charts of things like.
I think the Tableau demonstration, I guess.
Maybe it was in the Tableau demonstration. It was like charts of, I didn't write down the topics. Yeah, these things. What's included in this?
So these are just the test data.
Okay.
Yeah. So, and one of the things that I think is going on here, some of the categories seem to be missing, and that's because the one hot encoding seems to have dropped one of the categories, and then when I tried to reconstruct it, it lost the category name and it stuck them in with the rest of the no name categories. So I'll have to realign the data and take it before I did the dummy encoding of the data and use that as my X feature set for this.
And based on how much time you had, this is really, really good, because you really have to, once you see things, you find out more information, and then you wish you had time to go back and do things differently so that it would look a little bit different.
Yeah.
Yeah, you did a good job.
One of the things that I realized as I was, looking through the paper the other day was that in terms of what I had to research and explore, just to be able to, I wanted to make it so that I could explain everything, from a level of somebody who knows almost nothing about what's going on to knows everything about what's going on. So it's not really a scientific paper that would be published to peers, but really something that can be, explain every step of the process. So explaining things like variable selection, class imbalance, things like that. So I went back and found, tried to find the original authors for each of these techniques, and sort of read what they, were saying when they read these things. I think I have either 16 or 18 different sources for that. And so being able to go through and read the literature about how, these things came up through history was something that I wouldn't have really taken the time to do otherwise. So just based on, learning these things in the class, we got, maybe 1 or 2 days at most, focusing on these topics. And we just got, the basic overview, but actually getting to read what the people who were, researching these topics were thinking when they did that was interesting.
I think this is exactly what data science is trying to teach you. Like if you're faced with different types of audience, how to better demonstrate your result and speak a language what the audience is speaking is going to be very important. And I'm very impressed by what you have done in this project. To be honest, I was with you the whole process, but this is the first time I see the whole picture, the complete project. Some data is just like blow me out. Like for those race and affinity, the feature importance study you have done across all those kind of models, that's going to be very interesting. I'm particularly interested by two things. One is the feature engineering, how complex the process is. And the second part would be the data visualization you have done in Tableau. These two would be the two highlights I can see in your projects. And just speaking of the data preprocessing stage, I think you have used a lot of very, advanced techniques like doing the upsampling, downsampling, and you probably haven't noticed, but I think you're using the SMOTE technique to do the upsampling.
I didn't do any upsampling or downsampling.
Oh, you didn't do that?
I only used weights and boosting. I just
Okay.
wanted to provide those other options. So those were, and then I gave the drawbacks to those, showing why I didn't use them.
Okay, so you
overfitting and
you use a weight in order to adjust the imbalance in your data
yes.
set.
And
Okay.
if you look at the presentation here, you can see which models weights were used and which ones they weren't. And in some cases of logistic regression, the ones without the weights actually performed better, which was strange, but.
Right, I can only imagine if you just give me this list of models, how much time I'm going to take to, to fine tune each one and collect the result.
Yeah, and that was one of the things, if I had another semester, that's what I would have done, and then I would have had, models that had, instead of seeing this 81% as my best score here, maybe I'd be able to get to 90. I originally, when I gave the proposal, I'm like, my goal, I want to get a 93. I want to get a model that has an A as its rating, but that didn't happen. B is okay for these.
I think you just touched on a very important thing. Like in data science field, garbage in, garbage out, right? So if the data contains a lot of noise in itself, then there's no way for you to get a good, reliable model out of it. So yeah, if you have more time, I'll definitely suggest you to do more data preparation, clean the data, do more data, cleaning and transformation.
One thing that Deb mentioned was that the data is not the same across the years. So I would be interested if I did this ran all of these models over again and just did a random train test split with the same sizes of data to see what would happen. So if I took everything from 2009 to 2020 and just took like 3,740 examples as my test size, just randomly selected out of that what the results would be, just to see, if that influences it.
That would be a good idea. I think so. Yeah. So like randomize your data first and then do the split, right? Is that what you're speaking? Okay.
Yeah, and it might make more sense to once there's more data, if this were to be redone in the future, take only the data after 2018 when everything was sort of synchronized. So if we had maybe 5 years from 2018, so 2023, you'd have 5 years, you'd have enough to do like a 4-1 split or a 3-2 split.
I'm also very surprised by how comprehensive the data set is from our animations office. That's very good.
Yeah, I think that one's that's not in the PowerPoint, but it's here. I have every feature that was included, so all of those are in there, and then the source table and the type of the data is all there. The biggest part of the pre-processing for this was figuring out the right way to write these SQL queries to pull everything without having duplicate records, because we don't really use primary keys the right way here.
I'm just curious. how did we collect those data? Do we have like a person who enter those entries, or do we have a system to automatically collect those data and put that into the database? I'm just curious.
Do you know, or are you asking me?
Well, there's
Uh,
both. There's both, right? Because we have the batch jobs that are importing from Slate, and then I guess Common App was
Okay.
batch as well, and then anything I guess that was mail we would have to enter manually.
I see.
And process something to enhance and think about is in 2009, our processes were so different, and our incoming student population may have looked very different. We're offering different majors than we offered back then, and there's so many things that change in 21 years. Trying to shorten it up a little bit may yield different results.
Well, and another thing is we just this past year, all the departments changed. So this listing of departments is completely, inaccurate. That was something that I thought of again last night when we were talking about the honors and the discipline and figuring out, who's the chair that needs to sign off on this. Because last year it was somebody, now it's somebody, and could be somebody else. We don't know.
That's true. Very good job overall. I think that's definitely beyond the expectation of the honor thesis. Very good job.
Very nice.
And thank you, Debra and Lisa, for coming to the presentation today. And thank you for the instructions throughout this whole process.
Yeah, great job, Ian. I'm really happy I got to sit in. It's really impressive all that you were able to do with the data that was given.
Thank you, Lisa.
Yeah. And good luck in the future, whatever that holds for you.
Thank you. Yes, Deb, I yesterday I got a job offer and I'm going to accept it once I receive a physical copy. So
Excellent. Can you share where?
yes, so Siemens Healthineers in Malvern, and I'll be working as a research professional on the artificial intelligence for diagnostic imaging team.
He's going to work with a bunch of PhDs.
Yeah.
So
well, no. So I have to tell myself I'm working for them. I can't work with them. I'm not on that level.
You will learn so much. You will learn so much.
Yeah,
I believe so.
That sounds like a great opportunity.
I had my interview for that on Monday, and I found out yesterday. But it was interesting because I got to the interview and one of the people asked if I had prepared slides. I'm like, this is a job interview. What do I need slides for?
Well, they obviously have good taste and recognized talent.
Yes. Well, I had been working for another team under the same manager over the summer and over the fall. That was my internship, which took a lot of time away from this. Tuesdays and Thursdays were supposed to be my days to work on this project, and I got a little, involved with work, spending the whole day working and that kind of stuff. So this sort of culminated at the end of the semester. But I had applied at other places, and they approached me where I'm working now, and they said, well, we want to keep you. Like, what are the other places offering? Like, we'll match it or beat it. So
wonderful.
If they lose you, it's their loss.
Yeah.
Very good. All right. Thanks for the presentation. And
thank you.
I have recorded the video. I'll share the video with everyone else, and just good luck for your future.
Thank
you.
And
you still have one thing due to me, the final paper. So
for the other project, yeah.
Yes.
So with this, I have to get your signature and Dmitri's signature, and I guess Dr. Atwood's signature, or is it yours?
That's Dr. Atwood's.
Okay.
Mm-hmm.
All right. Thank you.
Good job.
All right.
Bye.
Take care.
Bye-bye.